Okay. What's a polynomial? Well, this is a polynomial. Okay. Now I could rewrite that polynomial using x instead of this Greek psi. To xi. Okay. Kind of pronounce it psi. Okay. For many reasons, because it relates to this geometric situation in that rotating thing and that cup that the penny goes into, if a miracle occurs. I didn't want to use x here, but I'm going to rewrite it. 3200 x to the fourth plus 900 x cubed plus 5400, 5400. And I'm writing x, right, x squared minus 440 x minus 3200 equals 0. Now this is a polynomial. Of degree 4. What's the degree? It's the highest power. Okay. And there's no fractional powers. There's not like an x to the 1/2 or an x to the 1/3. Okay, just plain old positive powers of x. And I'm going to pause for just a second. I realized that. Okay, I had to pause just to focus the camera a little better. Okay, so this is a polynomial degree 4 again. There's the degree. Now, if these are out of order, it doesn't matter. You just look for the highest degree. If I have the 5400 x squared first and the negative 3200 second and the x to the 4th third and then this is 4th and 5th, okay, it would still have degree 4. You'd still get the same numbers if you plug them in to the polynomial. Okay. There's a 0 near x equals 0.64. Okay. Now, what can we tell about this polynomial? We would like this polynomial to be in factored form. Okay. Where you've got like an x minus 5 and an x plus 2 and all that stuff. Okay. And we've seen that form of a polynomial. We have no idea how to factor this thing. Okay. Now, if it does factor, one of the factors should be close to x minus 0.64. Okay. Now I'm going to give this polynomial a name so I don't have to keep writing it out. The other advantage of function notation, you give the thing a name and talk about it. Okay. Well, in that case, x minus 64 should divide the polynomial. Remaining I'll say that P of X divided by X minus 0.64 equals Q of X. Polynomial. Three. Well, you already knew that, right? No. Okay, maybe if you've seen it already in your pre-calculus class. But this is real handy because it's pretty easy to divide this into this. So one of the things we're going to do is we're going to learn how to divide polynomial into a polynomial, okay? And see if there's a remainder. Just like long division of numbers, which nobody pretty much remembers because the last time you probably had to do it by hand was in 5th grade, okay? But we'll refresh you on it. All right, so that's one fact. Another fact is you count the number of times the sign of the term changes, okay? Between one factor and the next, when the factors are in decreasing order, or when the powers are in decreasing order, okay? That's at one factor, it's one term. Okay, so you put the terms in decreasing order like this is, you don't put X to the 4th in the middle with 3200, negative 3200 at the beginning, stuff like that, okay? So the number of sign changes tells you the maximum number of zeros, the maximum number of times the graph would cross the x-axis. And if you can find the zeros, then you can reduce the degree from 4 to 3. And then you can deal with the 3rd degree polynomial and see if it behaves. Okay, well, that's kind of an overview, and you haven't done any of that, so there's not much point in my talking about it until we look a bit at the mechanics. Another thing about this is part of this course, but it's really pretty useless. But we still have to do it, still have to test on it, because somebody thinks that this ought to be part of the course. It's kind of neat stuff. As a mathematician, I love it. And if you're a mathematician, are going to go into some pretty advanced stuff, it becomes important. But it can wait until you get there. Okay. And most of you are not going to get into mathematics past 4 semesters of calculus at the most. Okay. Most of you won't get anywhere near that. Maybe 1 semester of calculus or 2, depending on what you want to do. As an engineer, you would have 4 semesters of calculus. In almost every other curriculum, 1 or at most 2 semesters. And this is modestly useful in calculus, but it's not really that important. Okay, polynomials are important. All right, well, enough digression. Let's get to it. Let's say you have, and I'm not going to deal with this polynomial. I'm probably not even going to try to divide it by x minus 0.64. Okay, just giving you an idea, though, of how you could use some of the stuff that we're going to talk about. Okay, so the first thing we want to learn is how to divide a polynomial by another one. And x minus 6.64 is a polynomial. It's of degree 1. Okay, x to the first minus 0.64. Okay, so let's say we have another polynomial. I'll also call this one p of x because we're not talking about this one anymore. Let's say we have a p of x that's equal to x cubed plus 7x squared minus 5x minus 3. Okay. Now you can check if I substitute x1 for x, I get 1 here, and I get 7 here, I get 5 here, and negative 5 and negative 3, right? In those numbers, 1 and 7 add up to 8, -5 and -3 add up to -8. So 1 is a 0 of this polynomial. Make sense? Okay, now let's just see what that means. That means that this polynomial is divisible by x minus 1. That would be a polynomial of degree 2. So there's an algorithm for dividing polynomials. And I'm going to rely on open math to clarify the algorithm for you, but I'll demonstrate it a couple of times. How do you do that division? You write it out like a long division. Okay. Now, what do you get if you divide x cubed by x? I'm going to ask you to write it out on your paper. You know, x cubed divided by x equals what? Oh, man. That was a really good explanation, and I didn't record it. It's disgusting. Okay. The camera wasn't recording. My bad. I don't know where it started, where it stopped. But I'm going to start from the beginning. This thing here is a polynomial. It has to do with a rotating beam, a magnet on the end, penny on the magnet. If you rotate it too fast, the penny flies off. Well, last week, one day or the week before, I gave the thing a spin, demonstrating it to physics students. I didn't really notice that the penny had landed in that cup over there. Okay, well, here's a schematic. Thing is spinning like this. The penny comes off at a point here. Okay, and lands in the cup. Well, you can do a lot of analysis of this thing that you don't want to see, okay, because you got to use some trigonometry and a bunch of other stuff and coordinate plane, but you can understand that this point is going to have some coordinates, okay? So this point is characterized by, first of all, the radius of the circle and the angle. If you know the radius of the circle and the angle, you can find this point, okay? And this point I call x cup, y cup. A stands for the radius of the circle. So this big mysterious expression here, except for this Greek letter xi, this kind of weird looking thing, okay? I didn't want to use x because our x is in the coordinate system, okay? This weird looking thing comes out of the analysis. And you know you have the right angle if this thing equals 0. Okay, now if you know anything about trigonometry, this is just a sine of theta, but you don't need to know that because I'm not going to ask you to analyze this. Okay, but that's where this comes from. And you see, you got A's and Y cups and X cups. Okay, those are just the coordinates that we can measure with a meter stick. So you plug in what looks like the right values of A and the angle and so forth, and see if this is 0. Well, if you plug in A, Y cup, and X cup, everything but the size become numbers. For the prediction I made, or I thought the thing might have been, the numbers came out like this. So I had this polynomial. fourth power, the variable, third power, second power, first power, and the zero power, which is just one, just multiples of those powers. Okay, that's a polynomial. Now, I've rewritten the polynomial here, but I've used x instead of the Greek psi because that's hard for people to look at unless they get used to it. You look at an x, you're okay with that. Okay, now, say this is a polynomial of degree 4, okay, because the highest power of x is 4. Doesn't matter what order these things are in. I could change the order of these terms. It would still be a polynomial of degree 4. So it's not necessarily the first term you see, it's the term with the highest power. However, when you do polynomial, you want the highest power first and so forth. You want it in order of powers so you can see it better, so you can understand what you're seeing. And it's really, would be very inconvenient to deal with it if the powers weren't in decreasing order, okay? So that's a polynomial of degree 4. From my estimate of where this thing was, when it looks like the penny should have gone straight to the cup, I estimated this angle theta here, and I took the sine of that angle, and I got something like 0.64. Well, if this thing is 0, then you have the right angle for this. Okay, it's a little complicated, way complicated from the point of view of pre-calculus student, okay? So you don't need to understand how this came from that, but there it is. And what we want to test is whether that's 0. One of the reasons we want to test it is there's no way that happened, but it happened, okay? The physics tells us that it's totally impossible that happened. And we're still looking for an explanation. We got a whole semester's worth of experiments we could do to test various possibilities, but I can't see how any of them are going to work out. It's a total mystery, which is kind of interesting. Okay, so there's a mystery involved with this polynomial. If we do plug x equals 0.64 in, we get a total here of maybe something like 100, not 0. But compared to these coefficients, these numbers here, 100 is a pretty small number, isn't it? Compared to things that go up almost into the tens of thousands, it's pretty good. Okay, we're still searching. Now, you could put this thing into a computer algebra system and get a very accurate approximation of where the zeros are, okay? So you ask, why would you do that? Well, because it gives you insight into things that you wouldn't otherwise have insight into that might be helpful to you in calculus, especially if you take a engineering type calculus course. And some of you might do that. All right. So the polynomials that we've seen so far have all been factored form, like x minus 2 times x plus 6 times x minus 4. Okay. And you know that each of those factors can be set equal to 0 and give you a number that makes the whole polynomial 0. Because if you got factor times factor times factor, one factor is 0, the whole thing is 0. So it's really useful to be able to factor these things. Okay. However, it's usually impossible. So in some ways, this is sort of useless, but it's in the curriculum and we've got to do it. And I probably want to do a little bit of it anyhow, because the thinking process you have to go through sharpens you. Okay, so if this polynomial factors, I'm going to say that one of the factors should be close to x minus 0.64 because you should do x minus a number that makes it 0, then x minus that number is going to be a factor. Now 0.64 is not exactly a factor, but it's going to be close. Okay, so I say in that case, this should divide the polynomial without remainder or I should say with a small remainder, because I know it's not exact. And I know when I plug it in, I get something that's pretty close to zero, okay? And that means then that P of X divided by X minus 0.64 is what I'll just call Q of X. I got to give it a name. So I'm just going to say Q of X. And Q of X is a polynomial of degree 3. Because when you divide a polynomial of degree 4 by a polynomial of degree 1, if it divides evenly, you get a polynomial of degree 3. You lose 1 degree of the polynomial. Now, I'm not going to talk about this anymore. We're just going to do a simple example. Okay, this P of X equals X cubed plus 7X squared minus 5X minus 3. We can easily see that if X equals 1, this is 0. Because if X equals 1, that's 1, and that's 7, so that adds up to 8. But that's minus 5, and that's minus 3, adds up to negative 8, we get 0. It follows that this divided by this should be a polynomial of degree 2. Okay? Because we divide by X cubed by X, we get X squared. Okay? Comes down to that. Well, we can do that by long division. Here's a long division. We have X minus 1 divided into this. First thing we do is we say, well, if we divide X into X cubed, we get X squared. Okay? Then if we multiply X squared by X minus 1, we get X cubed minus X squared. Now this little red minus and this little red plus remind us that we have to subtract this from this. Okay? You want to have that reminder in there, but you don't want to write it down with the wrong sign. You want to write it down correctly. X squared times X minus 1 is this. And then you maybe put a little circle around the actual signs you're going to use when you put these together. So that X squared minus X cubed gives you 0. You don't have to do anything. And notice I got lines here. I talked a little bit about, why I suddenly think lines are a good idea. These lines keep everything lined up. So that all the X squared, everything below this line, as you can see, has an X squared on it. Okay? Or everything between these two lines. Everything between these two lines has an X on it. Everything between these two lines is just a number. All right. Okay, so now we've got everything lined up. We've divided X into X cubed to get X squared. We've multiplied X squared by the divisor, we get this. And then we write a little minus and a little plus because we're going to be subtracting. So that X minus X cubed is a 0. 7X minus a negative X cubed is the same as 7X plus X squared, not X cubed. 7X plus X squared, which gives 8X squared. Okay. Well, then we divide X into 8X squared, we get 8X. By 8X by X minus 1, we get 8X squared minus 5X. Sorry, we get 8X, we get 8X squared, no. Yeah. We have the X squared here, okay? And I didn't even have the 5X in there at this point. When I multiplied the X squared, 8X by the X minus 1, I got 8X squared minus 8X. Then I immediately put little circled signs on there to tell us what we're going to do. And that 8X would add to the negative 5X, okay? We don't even really need to write it down here, but we do write it down because that's what we traditionally do. And it's easier to see it if it's here and not way up here. Okay, this is just the same as this. We just bring this down because we know we're going to do the negative 8X and add or the subtract from the negative 5X. Well, we do that. And that really comes out 5X minus negative 8X is 5X plus 8X, which is 3X. Okay, then we can multiply 3 by X minus 1, we get 3X minus 3. If we hadn't already put this 3 down here so we can line it up easily, we should. And then, I didn't do it before, but I should. I will. well, it's got minus sign here. It's supposed to be a minus sign. Add a little plus sign here to indicate that this is 3x minus 3x, which is 0. This is minus 3 plus 3, which gives us 0. So this is divided evenly. Okay. That's the process of long division. So what does this result mean? Well, this divided into this gives you this, because this times this equals this. That tells us that x cubed plus 7x squared minus 5x minus 3 equals x minus 1 times x squared plus 8x plus 3. All right, what good is that? Well, we want to find typically when a polynomial is 0. Remember that that's what we ultimately wanted to do with that big polynomial and psi. Okay, and we're not going to actually do that. But you know, we want to find when the thing is 0, and that's something that frequently comes up. It's important to understand at least that setting a polynomial equal to 0 gives us important information about the polynomial. Okay. Solving this equation gives us important information. Well, if this equals this, then this equation where this is set equal to 0 is equivalent to this equation where this form of the same thing is set equal to 0. Since this equals this equals 0 is the same thing as saying that all this equals 0. Now we're used to the idea that if you multiply a bunch of things together and one of them happens to be 0, the whole thing is 0. Okay, multiply by 0, you get 0. It follows then that either x, if x is a solution to this equation, it's either the solution to x minus 1 equals 0. In other words, you want a number that makes this equal 0, or you want a number that makes this equal 0. Okay? It's not and. You can't have a number that makes this 0 and makes this 0. Because it's different numbers. It's, this is equal to 0 or this is equal to 0. So we write this with a big capital or. Solve this equation. Well, that's one step. Add 1 to both sides. You get x equals 1. Okay. That kind of confirms what I said over here. That because x minus 1 divides this evenly with no remainder, 1 does make this 0. All right. Now, so x minus 1 could be 0, or x squared plus 8x plus 3 could be 0. Now, x squared plus 8x plus 3, we might be able to factor that into two factors. And then each factor would give us a 0, just like the x minus 1 here gave us a 0. Okay? Well, you're not going to be able to factor that. Okay? Even if you're really good at factoring trinomials, it's not going to work. Okay? So we use quadratic formula, which is always available and always works. Doesn't always tell us what we want to know. And that doesn't always, the answer is not always what we were hoping for, but it does always give us an answer. So we just use the quadratic formula to solve this. We get this, which simplifies to this because it's is. You know, I screwed that up. Talk about negative signs messing things up. This is 64. That's minus 12. I just added 12 because I wasn't thinking clearly, and then the stuff I did down here doesn't apply. And these answers aren't right. So I just get rid of that and fix them. Okay. That's 64 minus 12, which is 52. The numbers aren't going to be what I said they were. Okay, well, 52 is 4 times 13. I can write the square root of 54 then as the square root of 4 times the square root of 13. The square root of 4 is 2. Okay, so now I've got negative 8 plus or minus 2 square root of 13. And that equals minus 4 plus or minus the square root of 13. And the square root of 13 is around 3.7. Maybe closer to 3.6. Yeah, I think it's closer to 3.6. But I'm just okay. So -4 plus 3.6 is negative 0.4. And that's what we get for the plus. And -4 minus 3.6 is negative 7.6. And I'll write approximately. I won't write out the whole word, but then I will put the R in it approximately. That's what it says. What it specifies that those aren't exact numbers, those are approximate. Put the number, put this calculation into your calculator, it'll give you 10 significant figures, 10 digits or so. Okay? And if you got a pretty good calculator, you could ask it to give you 50. It's never going to be exact. Now that's just done in my head, so it's highly suspicious. You would not want to accept that without checking it, right? And you probably double check it. And then you plug these numbers back into the equation and see if you get 0. Okay? And we could do that, but we lost a little time because I did that whole explanation without recording it. But I think it's worth seeing twice. Okay? Gives you the picture of what's going on with a lot of what's going on with polynomials and why we do it. All right, now. Best way for most people to understand a function is to understand its graph. So what's the graph of, I'll say y equals, so we know that we're going to use the y-axis. We're going to label the vertical axis y. Okay. Viewed from far away, graph looks like this, approximately, has this basic overall shape. Okay. Now, if you're not too far away, you might notice, you might be able to just barely see that there's some little wiggles in here. They're close to the origin. Now, when you zoom in closer, so we take this little part of the graph, and we're going to take this and we're going to construct it down here. There. Okay. Going to be this. We're going to locate the zeros. Okay. Because the wiggles all occur close to these zeros. You'll see why in a minute. The zeros are at 1, -0.4, and -7.6. So we're going to occur mostly to the left of the y-axis. So I'll kind of extend the left part of the y-axis. The biggest number we have here is 7.6. Of course, it's -7.6. But I'm going to say that, okay, let's say here's -8, which is close to -7.6. If I divide that in half, I get x equals -4. Divide that in half. I get x equals -2. I have a negative sign. And over here, I'll have x equals 2. Now you could line the thing off, count from -10 to 10. That would get you enough, but you want a scale that's big enough to accommodate all the zeros. Okay? Now I'm going to ask you to calculate something because you've been listening to me going on for a while. If x equals 0, what is y? Okay, what we've done. And of course, I'll have the other video before this one, where I explain all this in detail. We've started with a real life situation where something really weird happened in physics lab. Okay. It involves motion around a circle and something flying off and flying into a paper cup. We get this polynomial. The meaning of this polynomial is if this squiggly thing, which we call a psi, it's a Greek xi, is the way we spell it, is just right, so that this equals 0, then we know the angle at which the thing flew off, and we can then proceed to figure out all the laws of physics seem to be defied. The gremlins must have thrown it. But it's kind of a mystery. Okay, well, that leads to this polynomial degree 4, et cetera, et cetera. And if x equals 0.64, which is an estimate I made of where the thing was, then if x equals 0.64 is actually a 0, then this polynomial should be divided by x minus 64 and gives you a polynomial without remainder. Okay, now I did all that in some detail, and you get that in the preceding video. So here's how we divide it. We do a long division, and we determine that x minus 1 divides into this x squared plus 8x plus 3 times. Now this is not this polynomial. This is the one I made up, and I made it up so that it would be 0 when x equals 1. So we divide this by x minus 1, we get this. Okay? Now, since it's 0 when x is 1, I divide by x minus 1, and I know that if everything's been done correctly, that this is going to come out with no remainder, which it did. Okay, then we know that this polynomial is x minus 1 here times this remainder, or this quotient. So that if we want to find out when this polynomial is 0, we can write it like this, because this times this has to equal this. When you divide, this times this has to equal this. Okay. This splits into 2 equations. Still recording, yeah, I'm getting paranoid. Okay, we have x minus 1 times x squared plus 8x plus 3 equals 0. Splits into the equation x minus 1 equals 0. Or the equation x squared plus 8x plus 3 equals 0. If this is 0, the whole thing is 0. If this is 0, the whole thing is 0. So we set this and this equal to 0. And solution to this or a solution to this is going to make the whole thing 0. So we use a quadratic formula to solve this. This is solved instantly. And we get these results, 0.4, negative 7.6. Now what we're doing is we're trying to make a graph of this polynomial. Not that 4th degree polynomial over there that we talked about, just a 3rd degree polynomial. Okay, so there we have it. We want to find the graph. Well, what do we know about the graph? We know if we look at this from a distance, since x cubed is our leading term with the highest power, we know that if we view this thing from far away, the graph is going to look just like the graph of x cubed. Okay. That's a distant view. But if we zoom in just a little bit, we see that the thing does deviate in here near the origin, and you get some wiggles there. Or you can get some, you don't have to get wiggles, but you can. Well, in this case, you have to get wiggles because this thing is 0 when x is 1, or when x is negative 7.6, or when x is equal to 0.4. Well, we set the graph up. Okay, so it's set do a set of coordinate x, and I've circled the region of the wiggles. Put a little arrow down here. So we're zooming in on this little part of the graph that deviates from the x cubed graph by a little bit at least. Okay. I'm going to line this off. My zeros are at 1. And that's exact, but then we have negative 0.4 and negative 7.6. Make ourselves a note that these are approximate. Then we locate these x coordinates, because these are x values that make y 0. We locate these coordinates. So, okay, so this point would be 0, negative 7.6. Okay, we have another point at negative 0.4. That's real close to the origin. I wrote these backwards. Be negative 7.60. I do that a lot if I'm not paying attention. Negative 0.40. That's here. And 0, 1. Now, if this is x equals 2, this will be x equals 1. Okay, and that's going to be 1, 0. Now, the question is, the thing looks like this, but when we get close to the origin, within 10 units or so to the right and left, we have to go through the y-axis or the x-axis here. Now, I did ask the question, if x is 0, what is y? What did you get? X is 0. Well, look, if x is 0, this is 0, this is 0, and this is 0, right? They've all got x's in them as factors. That leaves us negative 3. Make sense? That means our y-intercept is at negative 3. So I'm going to draw a line here. Label it y equals 3. I like to use fairly long dotted lines to label coordinates so that the labels don't get in the way of the graph. I kind of recommend that, although if you're in somebody else's class or go into somebody else's class later, they might think that's kind of weird. There's pretty good reason for it though. Okay, so anyhow, what has to happen now? You're coming up from here. You're coming up from here. You get to your first 0 is here. Okay? You're coming up from negative values because that's what you get for y equals x cubed. Coming up from here. So you're going to go through the x-axis here. And you're not going to go through the x-axis again until you get here. Oh, come up here pretty high. Then you come back down right through the label I was trying to miss. And now you got to turn around pretty quick to get this, but you got to come down here all the way to x equals 3, so you're not going to turn around that quick. And you probably go through x equals 3, and then you come back up, and there's a little wobble in that curve that shouldn't be there. The curve should be concave up everywhere. Well, on this side, concave down here, so I kind of got a little wall in it there. But you get the idea, that's kind of what the curve looks like. And this point, of course, is 0, -3. Now you could estimate, how low do you think you have to go past 3 here before you turn around and come up here? What's that, maybe y is -5 there when x is 0.6? Okay. You can make that estimate, you can make an estimate here. But there's really not much point in doing that, even though it's really a lot of fun. You don't want to necessarily do that because when you learn just a little bit of calculus, you'll know how to calculate how high it goes here, how high and how low it goes here. You'll actually be able to calculate the coordinates, the high point and the low point. So if this thing is an important polynomial that tells you something, you'll have much more information about it at a better scale for it. Okay, so that's what we've got. We're still recording, good. All right. Now, you understand how long division could be really an advantage. And there's this thing called synthetic division that I don't even talk about. It's a shorthand way to do long division. So you're welcome to use that even on a test if you do it accurately. But I'm not going to waste any time talking about it because you're going to forget it before you ever have to use it again. And if you understand long division, it's real easy to figure out synthetic division. But it's quicker, just a quicker way to write all this stuff out. You don't write the x's, you just write numbers. And it's a pretty neat algorithm, but it's a really obvious one. Okay. So I think you need to remember long division. You're not going to remember synthetic division past, 2 weeks past the last time you use it. At least 99.9% of students won't. You remember there was such a thing, you won't necessarily remember. Okay. Let me pause for a second. Okay. When we divided this, there was no guarantee that this part of the quotient, the x squared plus 8x plus 3, would give us a real number. Because you know that any quadratic could give you a negative under the square root, depending on what the coefficients are, right? So if you've got a negative under the square root, this thing would only have 1 0. Okay? So it's possible for a polynomial of degree 3 to have 3 zeros. Means it factors into x minus this, and x minus that. It's also possible, well, okay. I could write this. This polynomial factors into something that's kind of close to this. Why? Because it has a 0 at x equals -0.4. Okay, this would give you a 0 at -0.4. This would give you 0 at -7.6. Now remember, those things are approximations. Could be off by even a tenth. Your calculator could give you an approximation down to the trillionth. Okay? But it'd still be an approximation. Nevertheless, there is some number where this thing passes 0. There is some number really close to here where the thing will be 0, and a number really close to here where it will be 0. Okay. So we have 3 linear factors, 1, 2, 3. Each gives us a 0. What if some function q of x was like this? When you do the discriminant, you get b squared minus 4ac. 4ac is going to be 4 times 8, which is 32, and you're subtracting it from 3 squared, which is 9, and you get negative 23 without doing all the details substitution. You can do that yourself and verify it's true. This is not a real number. So q of x equals 0 when x equals 1 and nowhere else. So now what does your graph look like? Well, we're out of time. But here's your 0. The graph looks like this, and it doesn't have to wiggle. Maybe it does, and maybe it doesn't. But unless you know calculus, your best guess is just a guess. Probably comes up from here and flattens out and goes on and goes through the x-axis there just one time. Okay. Another thing, you're coming up from here and ending over here. If it goes through twice, it has to go through a third time. Well, not really, because the third time, it could be shaped like this. If I raise this up just about 5 units or so, this kind of a vertex here could be sitting right on the y-axis or the x-axis. Okay. So that's possible. So you could have just 2 points where x equals 0, but one of them would be where the function is like a parabola. Okay, well, the open math assignments that are coming up will fill in a lot of details about what I'm just talking about. Okay. And if you're in a course where you're actually studying this stuff, hopefully that overview gives you a context. And what I'm trying to do right now is figure out how to catch up to where other courses are. Okay. Because distance courses go on no matter what happens. So all the disruptions we had in the last couple of weeks probably put us behind distance students. And even the in-class students are moving through this stuff at a little different pace. We were unable to stay ahead of them. Okay, so we're going to try to catch up and then get on to the really important stuff.